Bon dia, benvinguts a una nova edició del col·loqui FMUPC, que aquesta vegada hem pogut organitzar, tot i que una certa premura de temps gràcies a les gestions que ha fet el professor Xavier Cabré. I de fet, com que és un tema molt interessant pels estudiants de l'assignatura que ell imparteix, que és EDP, doncs per això l'hem posat en aquesta franja horària. For us it's a great honor to have you here today, and we are very happy that you accepted to give the conference here. I res més, no vull allargar-me perquè tenim poc temps, o sigui que li passo la paraula al director del departament que faci els agraïments oportuns a la comissió, etc.
Doncs reiterar la benvinguda a tothom. I també la mateixa idea que deia el Jaume, de que potser no tenim tot el temps normal, doncs agrair al comitè organitzador per una nova edició d'aquest col·loqui i quasi que passo la paraula a Xavier perquè faci la presentació del comitè.
Bé, simplement, molt ràpidament, només un apunt bibliogràfic, és el que hi ha en l'anunci que vam escriure fa uns dies. Tobias Colding was born in Copenhagen, received his PhD in 1992 at the University of Pennsylvania under Chris Kroc. Since 2005, he's professor at the MIT, and he was also faculty at the Quran Institute in New York University in various positions from 1992 to 2008. He's been invited address at the International Congress of Mathematics in Berlin, 1998, and has very important works in geometry, more specifically in minimal surfaces, with his collaborator William Minkowski, first on harmonic functions, then on minimal surfaces, as I mentioned. And he's now working on an equation that he's going to talk about related to the mean curvature flow. And he's been Oswald Verlin Prize in geometry for his work on minimal surfaces. So thanks for coming. It's a pleasure to have you here, Tobias, and we are looking forward to your talk. Thanks.
Hello. Okay. Yes, thanks very much for the invitation. It's nice to be here. So I will talk about what's called the level set methods and the level set equation. And I want to talk about optimum regularity results for this equation. So when you model various physical phenomena, then it often leads to tracking a front that is moving with a curvature-dependent speed. When the speed is a curvature itself, then it leads to one of the classical degenerate nonlinear differential equations, and one naturally wonders what are regularity of solutions. Right, so I'll get into this in a second, that previously solutions was only known to exist in a weak sense. And one wonder if that is necessary. So optimal regularity, that's a kind of classical question for this equation. And if time permits, then I will also talk about, and time may not permit, but if time permits, I'll talk about, even though that solutions, as it turned out, only have low regularity, is it still possible that solutions could behave as if they were analytic functions? If this was the case, then this would answer various questions. If we have even more time, then I will also talk about other equations. So I think these techniques and ideas that I want to discuss here, I think they should be applicable to a range of equations. And so I'll give some examples of that, if time permits. So here's a sort of classical scenario. This picture is not all, but a number of the illustrations are borrowed from Jamie Session. So this one is borrowed from Jamie Session. So here you're looking at a forest fire, and you try to track the perimeter of the fire as it evolves. Right? And so you see that initially here the fire has two different components. Over time they may merge, and so the perimeter here, starts off being disconnected. Over time they connect. So that's one example of tracking an evolving front. Here's another example where you have oil droplets on water. So you can track the evolving front of all the different droplets. And so here, droplets could merge. So it looks like these two are maybe about to merge. These here maybe have just separated, right? So they can separate and merge. That's another sort of classical situation where the level set method have been used. So the level set method, I'll get to that in just a second, is extremely widely used in, not the least, in applied mathematics. The particular equation I'll look at is this equation. So this is a degenerate elliptic equation. So it's quite nice. As far as a degenerate equation, it's quite nice. It's obviously modeled by the Laplacian. And so, so you have this function u is defined on some compact domain in Euclidean space, and you are interested in solutions to this, and typically you're interested in solutions that are constant on the boundary. Okay? So it's constant on the boundary, so this means that, and it's not a trivial solution, right, obviously, it's great, because the whole thing has to be -1. So the function, so it's a compact domain, it's defined as constant on the boundary, so there must be some critical point in the interior, right? And so at the critical point, this equation, of course, is degenerate, because you're not really allowed to divide by 0, right? And so this is the equation, this is the elliptic equation that we want to focus on. There's a corresponding parabolic degenerate equation, where this here is applied by, it's replaced by, the left-hand side is replaced by a time derivative of u. Okay? And so the optimal result that we have, and so this is indeed optimal, so this is for this equation that has again been widely studied. So the optimal result here is that solutions are always twice differentiable everywhere. So if you look at this equation, if you are away from critical point, then regularity of this equation is a kind of classical problem. It's known to be smooth. But so the question is really, what is the regularity of solution at critical points?
One question,
So,
the level sets of U would be the evolving front?
That's right. Yeah, that's right. So in a minute, I'll get back into how this particular equation is connected with tracking the evolving front. But I just want to give you the equation first, and I first want to give you sort of the main result about the optimal regularity of this, and then we'll talk about where does the equation come from, and so on. So again, the optimal regularity result is that solutions are always twice differentiable everywhere, and at critical point, the Hessian is in a very simple explicit form that I'll get back to what the form is. Right, so this is, again, it's one of the classical degenerate elliptic equations. It was solved a little more than 25 years ago. It was found that solutions exist in the viscosity sense, so this is a weak sense. So it was proven that this equation has weak solutions a little more than 25 years ago. And it was also proved that those solutions were Lipschitz. Right? But it turned out that they're not just Lipschitz, they actually are twice differentiable. And at critical point, you know exactly what the Hessian is. So, so it turned out that not only are they viscosity solutions, but they're actually classical solutions. It's really an optimal regularity result because the second derivative. So this result say, of course, that the second derivative always exists. It's in fact always bounded. But in general, it may not be continuous. And we can completely classify when the second derivative is also continuous. And so I'll explain this more, but this is just to kind of give you an idea of where we're going. So, right, and so the point here is that in order to prove optimal regularity, we have to really understand the underlying geometry. And I think without really understanding the underlying geometry of this equation, there's no hope of proving optimal regularity. And the ideas that go into the proof is a kind of mix of, well, of course, there's analysis, but in addition to analysis, there's also geometry and also some ideas from real algebraic geometry. So this is all joint work with Billman Cutty. And so, so again, if we have time for it, then I will talk about some further development. So some of those further development connects with catastrophe theory and singularity theory. And I think is a first instance of a general principle that solutions to many degenerate equations should behave as if they're analytic, even though they're not. Right? So we know now that solutions in general are only twice differentiable, but I think that I hope to be able to convince you that they probably have, even though they're only twice differentiable, they probably have analytical properties, even though they're not analytical functions. And so if this is part of a more general principle, then this would explain various conjectural phenomena. Okay. So now let's come back to where the equation comes from. So there's two ways of kind of thinking about the equation. There's a geometric way and there's a more analytical way. So let's think about it first geometrically. So suppose you have a hypersurface in Euclidean space. Suppose that n is the unit, and I should also say that my hypersurfaces are compact and they're always embedded. Okay? So they don't have any intersect, they don't cross itself. N is the unit normal. H is the mean curvature, sometimes called the mean curvature scalar. So that's the divergence of the unit normal. So this just means that you're taking the sum of the derivatives of the normal in the EI direction. So EI here, so you are evaluating the mean curvature at a point on the hypersurface. Then you take, at that point, you take an orthonormal basis for the tangent space of the hypersurface. This is the EI. And you take the derivative of the unit normal in the EI direction. You take the inner product with EI and you sum of I. Right? That's a mean curvature scalar. For a physicist, by the way, for a physicist, H here is really, you would think about H as a surface tension. Okay, so this is a very natural also, quantity. It comes up in many different physical phenomena. If you think about it kind of a little bit more analytical, you may think about the hypersurface as a level set of a function. So you take a function u, Euclidean space, and let's say that S here is a regular value, so the pre-image of S is a nice hypersurface. Then the unit normal is just the normalized gradient. The mean curvature is the divergence of the normalized gradient. The mean curvature flow is then so a one-parameter family of hypersurface is said to evolve by the mean curvature flow if at each point the time derivative of the position, so the point here is moving, and the time the speed here that it's moving with is minus the mean curvature, and it's moving normal to the hypersurface. Right? So that's the mean curvature. If the one-parameter family of hypersurface is flowing by this equation, then we say that they flow by the mean curvature flow. And so in this picture here, you see that that if you have a convex point like this under the flow, this here will move inward. A concave point here will move outward, right? So that's what happened under this equation. So you see already from this sort of picture here that this flow has some kind of smoothing property, right? That it turning in convex point becomes in a way more convex. Concave points become less concave, right? So it has a smoothing property, and there's a good reason for that, because this equation is in fact a geometric heat equation. Okay? So this equation had been studied for just a little over 100 years. It was first studied in mathematics in the 19-teens by Berkhoff, and it was independently studied already, perhaps before, but certainly already in the 1920s in material science, right? And so here, in material science or in the physics literature, H is called the surface tension, and this flow has the property that area or volume is decreasing under the flow, and it's decreasing in the most efficient way. So it's moving, the hypersurface is moving in such a way that the area is decreasing the fastest. So this means that physical terms, right, the surface tension is going down. Okay? And so the simplest example of mean curvature flow is, suppose you're looking in our tree. If you take a one-parameter family of round two spheres in our tree, T here is thought of as time, and it's negative. And so if you're looking at the one-parameter family of two spheres, round two spheres, they're all centered at the origin, and they have radius square root of minus 4t. Then this one-parameter family is flowing by the mean curvature flow, and you see that over time the radius is shrinking, and in finite time it becomes zero. Right? So in finite time it actually somehow collapses to a point, and then after that it disappears. Another simple example is the one-parameter family of cylinders. So this is again in R3. So if you take round cylinders where the radius of the cross-section of the cylinder is square root of minus 2t. T is again negative, so cylinders of smaller and smaller, with smaller and smaller cross-section or radius. Then you see that over time the radius is shrinking, and so at time t equals to 0, the cylinders have shrunk to a line, right? And so, and then after it has shrunk to a line, it ceases to exist, right? So in both of these examples, these one-parameter family of surfaces are singular at t equal to 0. T equal to 0 at the spheres becomes just a point. At t equal to 0, the cylinders become a line, right? So they're singular, they're not anymore a smooth surface, right? And so in these two examples, you have finite extinction. So here is just illustrated, the round two spheres, they're all concentric round two spheres over time, so time is going in this direction, the radius is shrinking, and it eventually becomes extinct at a point. Here you have the round cylinders, the radius of the cylinder is shrinking, and they become extinct in a line. It's an even simpler example, but it's not very interesting, so I didn't have it, but that's one have in a family of planes. They're not very interesting because nothing is happening. The mean curvature is 0, so they're static under the flow, so nothing actually happens. Right? And so, two sort of very simple key property of the flow is that so the mean curvature, you can think about the mean curvature as the gradient area. And so this means that the mean curvature flow is the negative gradient flow for volume. So it means again that the volume is decreasing in the most efficient way under the flow. The other simple property that the flow has, it's what's called the avoidance principle. The avoidance principle is responsible for exactly what we saw here in these solutions here. In finite time, the flow becomes extinct. I should say one thing here is that I said in the beginning that my hypersurface will always be embedded and always be compact. Of course, you may disagree. This here is not compact. It's not compact, but but later on, what I'm interested in a closed hypersurface, and I want to flow that, and I want to understand what happens to the flow of that. But even though that initial hypersurface is compact, if I try to focus in on a singularity and I rescale space around that singularities and do what's called a blow up, it's just where I kind of blow space up and I also rescale time as I have to for a parabolic equation. Well then, even though I'm starting with something compact, I may get something non-compact, and that's where this here is not particularly relevant for that, but the cylinders are very relevant for that. Well, the plane is relevant, but it's kind of a trivial case. Okay, and so, but I claim that it becomes extinct in finite time is a particular case of a more general principle, which is called the avoidance principle. So the avoidance principle is just a geometric formulation of the maximum principle, parabolic maximum principle. And so the avoidance principle will say that suppose you take two hypersurfaces, and suppose that those hypersurfaces are initially disjoint. So here it's illustrated with the red is one hypersurface, and the blue is another hypersurface. They are, of course, disjoint. Right? And now I start flowing these two hypersurfaces. I flow them at the same time. Right? So the avoidance principle say that if the two initial hypersurfaces are disjoint, then under the flow they will remain disjoint. Right? They don't have to. One doesn't have to lie in the other. It could lie, next to each other. That's fine. But if they're disjoint under the flow, they will remain disjoint. And this is just a geometric formulation of the maximum principle, and so you can sort of see that this will be the case from the following simple illustration here. So suppose that the red one, that is the outer one, suppose that it did actually cross the blue one, right? Suppose that they didn't remain disjoint, then the red one at some point must have crossed the blue one. But if it crosses the blue one, then there would be a first point of contact, right? It was a point where the red one was still lying outside the blue one, but just barely. It would touch at one point, right? So imagine that it's touching at one point, where the blue one is lying inside. It means that the blue one is more curved at this point than the red one, right? But this means that right before, the blue one must be moving at a higher speed, right? But this means that the blue one that they had already shortly before, they had already crossed each other, right? So that's a contradiction, right? And that's really just the maximal principle, right? But it's formulated here in geometric terms. But you will also write it down in terms of the equations, and you see that it's exactly the parabolic maximum principle. Okay, so now, so this is the flow. So at the moment we're talking about it kind of in geometric terms. We're talking about hypersurface. We have an equation that is in terms of the hypersurface. Shortly I'll get to talking about it in analytical terms. But so you may ask, well, let's see a little bit more general. The simplest example of the mean curve to flow is where the hypersurface is a curve. And so where you're looking in the plane, right? So that's the simplest example. And in that case, has been known for a long time, for more than 35 years, basically, 35 years. This has been completely understood. So in that case, the mean curve to flow is also the curve shortening flow. And so in that case, if you take the simplest example here, is if you take a round circle in the plane under the flow, it's shrinking through round circle and eventually become extinct in finite time in a point. There's a more interesting example. So this is this example of a sort of snake-like figure. So this is a simple closed curve in the plane. So imagine that you're taking a curve. So if you were to draw it, you take kind of a span here of the curve, and then you would wrap these two things around each other, and then you close it up like that. Right? So this simple closed curve is bounding this domain here, this compact domain there. Right? And so, well, the interesting thing is that under the flow, even a snake-like figure like this, but it's the avoidance principle saying that if you take a snake-like figure like this, you can encircle it by a circle, round circle. You already know that the circle become extinct in finite time. They won't cross each other, so the snake-like figure will become extinct in finite time, right? But what happened? You're interested in what happened before it became extinct. Well, so it's shrinking, right? And you see that this point here, for instance, at this particular time, and again, time is going from here to there, and then continuing on here. This point here is moving inward, right? So it's shrinking down. This point here, the end here, is moving at incredible fast speed because it's very highly curved out here. So it's this one here, it's moving inward, but this one is moving much faster this way. And so this is what is responsible for this picture, that this simple closed curve is shrinking, but it's actually unwrapping much faster than it's shrinking, right? And so this is a theorem of Math-Grayson from '89 that proved that any simple closed curve in the plane, in finite time, it will become extinct. But right before it becomes extinct, it will look like an almost perfectly round circle. And so what Math-Grayson actually proved, so he didn't prove this full picture, because he had the benefit of earlier work of Hamilton and Gage. And so Hamilton and Gage proved that if you take any convex curve in the plane, here the outer curve here is the initial time. And so the outer curve here is the initial curve. If you take a convex curve like that, then it will shrink and it will become extinct in finite time, and right before it becomes extinct, it will be an almost perfectly round circle. So that was Hamilton and Gage from '84 or so. And Math-Grayson in '89 was able to prove that for any closed curve, it doesn't need to be convex. Well, in finite time under the flow, the curve will become convex. And once it becomes convex, he would just appeal to the earlier result of Hamilton and Gage. So this pretty much closes the story in one dimension. So for curves in the plane, that's it. I mean, we completely understand it. The curve is smooth under the flow, smooth all the way up to the end. At the very last minute, it becomes extinct in a single point, but that point looks almost, what's called almost perfectly round. So there is a singularity, but the singularity is very, very nice. It looks essentially exactly as what happened to shrinking round circles. Okay? So this was known, again, 30 years ago. But in higher dimension, new phenomena happen, and so that's an interesting thing of the story. So, so here's a sort of similar example of something that can happen in higher dimension. If you take, so this example here is typically referred to as a merit ring. This is just a thin torus of revolution. Right, so it's the surface of this donut. And so in finite, under the mean curve of flow, the symmetry is preserved. So under the flow, it will remain a surface revolution. But in finite time, it will shrink again. The avoidance principle say that if you take any closed surface and you circle it by a large round sphere, the sphere will become extinct in finite time. This surface here is lying inside, it won't cross. So this here will become extinct in finite time, right? And so in this case, all that happened is the symmetry is preserved under the flow. So it will remain a torus of revolution. In finite time, it will become singular in a circle. So in finite time, it will shrink down to a round circle, and then it will cease to exist. Okay? Here's a more interesting example. This is an example also of Matt Grayson from '89, and this sits inside a family of surfaces that also has been completely understood for more than 25 years. But it's still a very constructive example. So this is a dumbbell. So this is again the surface of the dumbbell. So this is the initial surface. And you wonder what happened to the flow of this surface. This particular surface, so this is really the one that Matt Grayson look at. It's a surface of revolution, so it has this axis here that is a surface of revolution around. And then this particular example, again, of Grayson, has an additional symmetry, which is a reflection symmetry around the plane. So you ask, what happened to the flow if this is the initial surface? And what happened is that the neck here will pinch off first, and then the surface will be divided into two components, and then each component will smooth out and disappear in a point. Okay, so this is a computer simulation done for us, and so here, right, this is the initial surface. You see, this is at a slightly later time. The neck, everything has shrunk, but it looks kind of like as if the neck has shrunk the most, right? And here you see that the neck has just pinched off, right? And the heat equation takes over, it pinches off, and at the time that it's pinching, it becomes singular. The heat equation takes off over immediately, smoothing each piece. And so here, it doesn't maybe look very smooth, but it is actually, this time, it's a smooth surface. But it has very high curvature there, so it's moving very rapidly in this direction, that point here. And so that means that it's smoothing out, and so it's smoothing out, and I don't know, that maybe there's not more pictures, but if you had it more, you can imagine that these here would become almost perfectly round. Right? And so this here, so the lesson here is that you see that some new phenomena here happen when you're looking at the evolution of the dumbbell here, is that there's not just one singular time. It's a single time where the flow becomes singular, and then after that it becomes extinct. Right? Here there's a time where the flow becomes singular, and then the flow somehow still live after that point. And then there are two later, one later time, but two later points where the flow becomes singular. That's when each of these belts here is shrinking down to a point. Okay? And so this here is sitting inside a family of hypersurface that has been understood for more than 25 years. And these are hypersurfaces where techniques from one-dimensional heat equations are applicable. So this is hypersurfaces that are in, say, R3 and are symmetric around, so the rotational symmetric around an axis like this. Okay? If it's rotational, if it's an R3 and it's symmetric around an axis like this, then it's really just a one-dimensional problem. Okay? And so, right, so you could imagine not just the dumbbell we looked at here, you could imagine also a dumbbell with the belts have different sizes, or you could imagine many different belts and many different legs, right? But all lined up in such a way that the surface is rotational symmetric. And so this was completely understood by these two groups of people. So the first paper here, these papers here are more general than the Sonos Subinitas, but they both have versions of this. So so they proved. So again, so what the particular technique that they used here. So they understood exactly what happened, and this picture here is like what happened in general. I mean, so again, if you have more bells, joined by more necks, but it's all rotational symmetric, then you can have many different singular points in space and time. They're all isolated points in space and time where the flow becomes singular. Okay? And so what allowed to analyze this here is one-dimensional heat equation, and in particular, for one-dimensional heat equation, there's a Stormy-Will comparison of anchoring. He proved earlier a Stormy-Will comparison that is something very particular, one-dimensional. Okay? So, but nevertheless, the evolution of the dumbbell here is a good example to keep in mind. So this is kind of thinking about the flow geometrically. You want to think about the flow analytically, and in a way, you have to think about the flow more than what we did, because we thought about a flow, and I only actually defined the flow for a smooth one-parameter family, right? Because I talked about the mean curvature and so on, right? So, but you see that the flow here. So this is a computer simulation, so somehow you need to make sure that it makes sense to flow through the singularity here. And so there's at least three ways of doing that. And in the case of discuss, they are all equivalent. Okay? So there's three ways. There's a regularization idea that is due to the Georgia, and then there's a version, I think that's actually slightly older than the regularization idea, but that is due to bracket, that is using geometric method theory. And then there's a more PDE way, which is probably the most, in many ways, the clearest of the three. So, and that is the level set method. And it was not clear exactly when the level that method was first. It seems to appear the earliest in the material science literature, but it was made like a real method by Ocean Stettin in an extremely cited work of theirs from '89. And so the idea is very simple. So you now you have the mean curvature flow, I mean, and again, the mean curvature flow sits inside here in a larger family of flows, but the mean curvature flow is kind of the poster chart for this family of flow. And so the idea is, so you want to turn the equation into a kind of PD. Then you want to use the PD to talk about weak solutions. Okay. And so what you do is that you have a hypersurface and you want to flow that hypersurface. So now I want to find a PE that tells you something about the flow of that hypersurface. And so I choose a function that has that hypersurface as a level set. And then let's say that the function is positive in the domain that this hypersurface bound, and is negative outside, and 0, say, exactly on the hypersurface. Now you flow simultaneously every level set of this hypersurface. If you flow every level set of this hypersurface, then you get a parabolic degenerate equation. And this is this parabolic version of the equation that I looked at earlier. So this has been extremely successful numerically. There's all kinds of schemes to implement this numerically. So this picture here is actually taken from Wikipedia. So this is just how the level set method works. This is maybe you can think about the gray as outside the gray as a forest fire. The gray area is maybe where the fire hasn't yet reached. Then over time, you see that it reaches deeper and deeper inside the gray area, and they separate the gray area into components. And here is kind of this is the thing you want to track, the front you want to track, and here is how the level set method works. And so this techniques and sort of the numerical schemes behind it was initially explored by Usher and Sethian. The rigorous analytical foundation for studying this was done by Evans and Spook. So this is work independently of these two groups, Evans and Spook, and Giga and Godo. And so what they were able to prove was that this equation has continuous viscosity solutions. They were unique, and they agree with the classical solutions when the classical solutions exist. Okay? And so this was one of the major success of the theory of viscosity solution of Mike Crandall and Pierre Williams. Let me now specialize to the case where the initial surface is mean convex. So if the initial surface is mean convex, then Evans and Spook, Chen, and Godo. So they prove that if the initial surface is mean convex, the hypersurface is moving. It's moving initially inside itself. The maximum principle will guarantee you that if the initial surface is mean convex, then the later surfaces are also mean convex. So it moves initially inside itself, and it will keep moving inside itself. And so they prove that if you take a compact hypersurface, mean convex hypersurface, all of the examples I looked at, the dumbbell, the spheres, the cylinders, the Marriott ring, they're all mean convex. So if you're looking at a mean convex hypersurface, then it's moving monotonely inwards, and it keeps moving inwards. Okay, and it actually is sweeping out the entire domain at the initial hypersurface out. Okay, so this is taken from James Sethian. This is a computer simulation of the dumbbell. and this is the cross section. If you take the gradient dumbbell and you take a cross section of it, then that's how it looks like. And so here is like the initial. There's something funny here, but don't worry about it. It seems like it's crossing itself. It shouldn't be crossing itself if it were mean convex. But so this here is the initial hypersurface, and this here is at later times. Okay. And so if the initial hypersurface is mean convex, this leads to something called the arrival time. So the arrival time is just because if the initial hypersurface is mean convex, it's now moving inward, and it keeps moving inward, right? This means that, and it's sweeping out the entire domain that the initial hypersurface is bound. This means that if you are anywhere inside the initial hypersurface, in the domain, inside in the domain that the hypersurface is bounding, then there is some time when the evolving hypersurface arrived at that point. That's called the arrival time. Okay? And the arrival time, and so if you're looking at so the arrival time. The arrival time actually has, I won't really mention what this is, but there's a game theoretical interpretation. Yeah.
So the dumbbell that split into parts, that was not mean convex.
That is mean convex.
Huh?
Yeah, that is mean convex. The dumbbell that is splitting, this here is a dumbbell actually.
Yes.
And you see that, so this here is the initial time, this here is at a much later time, and you're here.
But fills,
Right.
so how it fills everything.
It fills everything.
Now it fills everything.
And so you see that and this here, you know,
Yeah.
this here really is also being filled up.
Yeah,
right?
sure.
But
No,
it's just, yeah.
I was worried about the
Yeah,
the
that's
center.
right.
The center.
Yeah.
Ah.
So I appreciate it's a kind of interesting picture that's going on here, right?
Yes.
Which is of course somehow related to some sort of tail expansion of the function, the critical point that we'll get to in a second. Right, so again, the arrival time has a, you know, as many of these problems has, it has a game theoretical interpretation that was found by Bob Cohn and Sylvia Saputin to a deterministic game. There was actually a game that was known already in the 70s by George Spencer. Anyway, but I won't really talk about what that game is. Okay, and the arrival time. Right, so I want to say just a couple more things. I want to maybe just go back here, and so remember that we talked about initially. I talked about this equation here. This degenerate elliptic PD. This here. Right, so this equation here, there's a parabolic analog where it's u, the time derivative of u over on this side. Right? When you're looking at, if you are doing the limited method, then you will arrive at this part in general, you will arrive at the parabolic PD. Right? That's exactly how you arrive at that parabolic PD. The thing is that if the initial surface is mean convex, then the parabolic PD is equivalent to an elliptic PD. That is a simple way of going from the parabolic to the elliptic. And so the arrival time satisfying this elliptic PD. Okay? So that's where this comes from. Okay? And so you see that you know, so this here, of course, I mean, you see that this is a kind of powerful, it's a very simple but powerful idea, because geometrically it's not so clear how do you define the flow past the singularity, right? I mean, you know, what is going to be the mean curvature if the surface is not smooth. It's not 100% clear, right? But you know, if you're looking at a PD like this, right, there's all kind of methods for defining weak solutions, right? Whether it's this elliptic PD or parabolic corresponding line. So this is in a way, it's I think this is an instance where the sort of analytical approach to make sense of flowing path singularity, that's the most transparent. I mean, again, there's two other ways of doing it. One using geometric methods, really, and another using regularization. Okay. So now let's go back to where we were. So we were looking at suppose you look at the shrinking round circles or the shrinking round cylinders. Well, for the shrinking round circles, the arrival time is simply this function here. For a shrinking round cylinders, this here is the arrival time. All you should take away from this really is, I mean, that's just a simple consequence of that it's spheres of with this radius, then you can just turn it into that. But what you should think here is that you have, in this case, we have just one singularity, this thing for the flow. The singularity for the flow is at the origin. In this case, of shrinking round cylinders, flow becomes singular in a line. Those are exactly the critical point for this function, right? So, in fact, this is a general fact that if you want to think about singularities, so you can think about geometrically, and then you think about it as where the surface is not anymore smooth, or you could think about it analytically. And analytically, the singularities are simply just the critical point for this equation, for the solution of this equation. And so this is this first dot here, but those are exactly the same points. The second dot is just emphasizing that you could think about this, but this is maybe a little unclear at this stage, but it will be clear in just a second. Why I want to emphasize this point is that you could think about this quadratic polynomial as the Taylor expansion of the function near the critical point. Okay, and the same in this case. Okay, and so again, the arrival time, it's satisfying if the initial surfaces being convex. You can turn this degenerated parabolic equation into a degenerate elliptic equation. This is the degenerate elliptic equation. This equation you can just rewrite like this. This is what Evans-Brooke, Schenke, and Goddard did in using this way of writing the equation. This here is admissible to using ideas from viscosity solution to define what it means to solve this equation weakly. Okay, and so that's what Evans-Brooke, Schenke, and Goddard did, and they proved that solutions to this equation are Lipschitz. Tom he was able to, he looked at exactly the example, this old example of, so this he did in his thesis, he was a student a long time ago of Craig Evans, and in his thesis he proved that Grayson's dumbbell that we looked at, that particular dumbbell that has two bells, has a plane that is, of reflection symmetry. And in that particular example, he could use a kind of balancing argument to prove that the arrival time in that particular example is not C2. Okay? And so here is again the optimal regularity that any solution to this equation, you're looking at, so when you're interested in solution to this equation, that is constant on the boundary. Okay? Corresponding to that the boundary is the initial surface for the flow. So any solution, so this will prove, any solution is twice differentiable everywhere, and at critical points, the Hessian, so this is stated in our tree, but it actually, we prove this in all dimensions, just for simplicity, I just stated in our tree. but we prove it in all dimensions. At critical point, the Hessian matches exactly the arrival time, the Hessian of the arrival time of the shrinking round spheres or shrinking round cylinders. Okay? And so again, so this here, so we know exactly at the critical point, we know exactly what Hessian is, so in fact we can conclude that solutions to this equation that was known to be just in the weak sense, in fact are classical solutions. So you don't really, in the end, you don't need the notion of viscosity solution. Right. We also have that, so the example of Tom already proved that in general, solutions, even though the second derivative exists, the second derivative may not be continuous, right? And so in fact, we can completely characterize when the second derivative is continuous. So earlier work on this, there's some earlier work on this, Priskin proved in 1990 that if the initial surface is convex, then the arrival time is C2. Sylvia Sapati and Bob Cohn proved that in the plane, if you take a plane, then actually the arrival time is C3. And Natasha Sesson proved 2008 that there are convex initial surface, so that the arrival time is, well, we know by Priskin that when the initial surface is convex, not mean convex, but actually convex. Convex again means, mean convex means that the sum of the principal curvatures is not circular, non-negative. Convex means that each of the principal curvatures is non-negative. And so this is much stronger. So Natasha Sesson proved that when the initial surface is convex, then there are actually sample of such surfaces where the arrival time is not C3. It is C2 of Priskin, but it's not C3. Okay, so now, so you may ask in general, when is the arrival time function C2? We know it's, again, we know it's always twice differentiable everywhere, but when is it actually C2? And so we can completely characterize this. And I'll state it just in R3, but our result hold in all dimensions with obvious modifications. So the arrival time is C2 if and only if the arrival time only has one critical value, and the critical set is either a single point, and in that case the Hessian has to be spherical, or it's a simple closed C1 curve, and in that case the Hessian has to be symmetrical, which means that it has one zero eigenvalue with multiplicity. Zero with multiplicity. Zero is an eigenvalue with multiplicity 1, and then it has another eigenvalue with multiplicity 2. And so in fact the kernel of the Hessian here is tangent to the curve. So you see that in the example that we looked at, the sphere, the cylinder, the ring, and the dumbbell. Well, the sphere, the cylinder, and the ring, the symmetric ring. In the case of the sphere, there was only one singular time, right? And there was only one singular time. There was also only one singular time for the cylinder and for the ring. In the case of the sphere, there was only, at that singular time, there was only a singular point. So we are in case 1. For the cylinder, we are in case, and this ring, we are in case 2. Right? Cylinder, we may say it's not exactly in here, but that's because it's not closed. That this simple closed curve is not closed here. Okay, so these three fall into one of those categories. But you also see that in the Matt-Grayson dumbbell, or any of those in this in this family of example analyzed by Altshuler, Engelin, and Giga, or or analyzed by Sola and Sovinidis. Well, in any of those examples, there are more than one singular time. So they don't fall into any of these two categories. And that's exactly because the arrival time is not T2. So, okay, so now, but now I want to talk a little bit. I also want to make sure that I don't go over, so I forget exactly when I started and how long I have.
5 more minutes.
5 more minutes?
Yeah.
Okay. I'll do it very fast. I'll just try to give you an idea. So how do you prove optimal regularity? What is the key point here? Right, so the key point is, so let's just skip a lot of things here. So the key point, so you want to prove that the function is twice differentiable. What does it mean for a function to be twice differentiable? Well, first of all, away from critical points, there's no problem, right? It's not, the equation is not degenerate, it's known classically, that is smooth. So you only need to look at critical points. But so at a critical point, you want to prove that the function has contact up to higher order with a quadratic polynomial, right? That's what you want to prove, right? And so, and so this quadratic polynomial is going to be exactly the arrival time of the shrinking round spheres or the shrinking round cylinders. That's a quadratic polynomial you're looking for. And so this is suggesting that you're trying to compare the level set of the function with cylinders or spheres. Okay? And so here's the key problem. And so it was actually known that if you go to a singularity, right before the singularity, it was known that the level set looks roughly like a sphere or roughly like a cylinder. So that's a good start. So this was known for a long time. But that doesn't give you, that doesn't really relate to differentiability. Because just remember that if you have a function of a single variable, when is a function of a single variable differentiable? At a point. It is differentiable at a point if on all small scales the function looks like a linear function, but it has to be the same linear function on all small scales. It can't look like one linear function on one small scale and then another linear function on another scale. If that's what you had, it would be like a fractional thing, right? It would be like a cut curve or something like that. And so this is the key. So this is the key, and so this is what you had to rule out. And it took us a long time. It took us more than 10 years. I mean, it was a known problem for many, many years. And so the problem here is that suppose that the level set on one scale looked like a cylinder near the singular point, which is supposed to be in the middle. Suppose that it looks like the level set looks like the yellow cylinder. But then closer to the singular point, it looks like the blue cylinder. And then maybe even closer, it looks like a completely different cylinder, right? Then you're shot. And so the question is, why should those cylinders be the same? Or are they the same? And so this is what we were able to rule out. And this is a kind of general question that is saturating geometric analysis, this kind of uniqueness of blow-up, and this is the first general instance where this has been proven. And this, again, this go over so we prove some new infinite dimensional Rashevitz inequality. Rashevitz inequality is something you have in real algebraic geometry, and we were able to prove it directly. There exist other infinite dimensional Rashevitz inequality, but they are completely unlike ours for good reasons. And so we had to prove our with bare hands, and so we were able to do it. Okay, so sorry.
Questions or comments?
Yes.
have been thinking all the time that could this be evolved in the other direction for some phenomena, like collapsing, I don't know, a pair of stars or something.
Right. That's right. I mean, so as you're suggesting, right? So the level set methods is very general, right? It just it talks about evolving fronts. So there's many equations that is fall into the mean curvature flow was kind of always the prime example of this. Also in the work of Ocean and Setien. But there are many other equations, of course. The economic equation is one that really looks like the forest fire, but there's also many other. And there's also many other that is kind of relevant to physics. So I don't know. I mean, we know that some of these phenomena, so what we have been interested in recently, and which there were some slides about, but of course I could never get to, was that you may ask, do these techniques also apply to systems? And so we have a natural system to look at is Ritchie flow. It's a system where the unknown is the matrix, it's a two-tensor. And so there we have results, these kind of results hold. And I think in many physical phenomena, the surface tension is the main force. So there I think you would expect things, but I think this should hold quite generally. I mean, it doesn't have, but exactly how general, I don't know. But it has to be some kind of parabolic phenomenon.
You said that in the dumbbell domain, there is no C2 regularity, because there are, I see, two levels, two critical values. So
right. So that's right. So
and what happens in the first?
So somehow sorry, I don't want to take too much extra time here from people, but if you went back to this example here,
yes,
then you will see that somehow that what we're really analyzing is we're looking at Hessian at this point, and we're looking at Hessian here. That's what you are looking at, and that's where you're getting the success. So we were able to prove, in complete generality, but it's kind of modeled by if you think about the Hessian at this point and at that point again.
Are you saying that at that point this is not a cone but a cylinder? And this is because of that?
I'm just saying that there's a jump. Somehow there's a jump. The Hessian jumps. It stayed bounded, but it's not. There's no continuous dependence on the Hessian, but it does stay bounded. We can prove that Hessian is always uniformly bounded.
The second derivatives are not continuous at the origin. Becomes like vertical and
Exactly. That's right.
And any other question or comment? Students can also ask.
Sure.
Yes.
Could this equation be modified to include some sort of force that keeps the surface from collapsing?
Right.
For example, bubbles or something like that, they don't collapse.
Yeah, that's right. I mean, that's right, and that is extremely natural. I think so, but I don't know, and I'm sure that it will require work, and probably also non-trivial work. I mean, to extend these ideas to systems like Ritchie flow is by no means trivial, okay, and also requires some new idea at the same time. And I mean, there's one particular flow, of course, a kind of well-known flow like that is like the volume of certain equals flow, and I don't know, I haven't looked at it, but I think it's, I think that sort of some of the basic ideas, it's not like you can just copy it over, right? But some of the basic ideas I think are quite robust.
But there are flows which are volume
preserving?
Yeah, there's a kind of standard flow that is volume preserving. That if you take some domain and you're flowing the boundary, and you make sure that that the volume of the enclosed is preserved.
The Ricci flow is used in the Poincare conjecture.
Right.
Is it kind of volume preserving or something like this, or?
No, it's not. But and so for the Ricci flow, for the Ricci flow, our results hold in all dimensions. So what we can prove at this time is that one of the key ingredients that get into the proof of this optimal regularity was a proof that Bill and I proved earlier in another paper, and was this, that the cylinders didn't change. But that proof there was an even earlier result along those lines that Bill and I proved with Tom Ilvenen, and that was that cylinders, for the mean curvature flow, cylinders in all dimensions are rigid as singularity model in a very strong sense, which means that if you take any other singularity model for the Ricci flow that is close on a compact set to a cylinder, then it must be a cylinder. That we later, maybe a year after we proved this with Tom, Bill and I thought about it in another way, and we realized that this result could be interpreted as some kind of result along the line that an infinite dimensional functional, which is called the Gaussian surface area, has some analytical properties. So came from that. We were then able to prove this Fourier-Shevitz inequality for this Gaussian surface area. So, but it's this first step that we can prove for systems, although I think that the uniqueness we will also eventually be able to prove for Ricci flow.
But can you tell us, you said solutions are not analytic,
right,
RC2,
right,
but they have properties like analytic functions. Can you tell us one, or
right. So more recently, so one of the, there's a lot of, I think, fascinating questions that are unknown that are common for all kind of parabolic flows. Similar things for dynamic flows, so one of the questions is whether conjecturally the flow should be smooth except at finitely many times. And so if you think about it in terms of the arrival time function, well, the flow is the singular times. That's exactly the critical values of the arrival time function. So you are asking, does the arrival time function only have critical, finitely many critical values, right? So if the arrival time function had been analytic, this is a standard consequence of being analytic. But in fact, and there's a sort of quantitative way of saying that it only has finitely many singular times. And that's a Fourier-Shevitz inequality. Fourier-Shevitz inequality is a quantitative, it's an inequality that has this as a particular application. And so for solutions that are C2, we can prove not only the Fourier-Shevitz inequality for the arrival time function itself, not for this other infinite dimensional function, which is some other kind of Fourier-Shevitz inequality, but we can prove the standard Fourier-Shevitz inequality. But we can also prove other things. We can prove what's called the Rennie-Thom gradient conjecture. The Rennie-Thom gradient conjecture came from Rennie-Thom's work in singularity theory, which is about gradient flow of analytical function. So he was interested in whether you had some more structure for that. And for analytic function, that was established in 2000. But we can prove it also for this degenerate equation. And then we can do it even one step further. We can also prove that what's called the Arnold conjecture, which was a generalization of the Rennie-Thom's gradient conjecture. And that one is unknown for analytic function. I mean, it's projected to hold for analytic function, but it's unknown whether it does for this equation. For C2 solutions, we can prove it. So we see that these are instances of this kind of general principle, that solutions for these equations, that have low regularity, you can kind of get optimal regularity result, but they actually has a lot of nice properties that they share with analytic function. And if this is really so, it would explain this phenomena. It also should explain various other phenomena.
There is no other further question. Let's thank Tobias again.